The following presentation examines lab number 3, black hole orbit. The purpose of this lab was to determine the mass of a black hole by using the known properties of a star, which is in elliptical orbit around the black hole. The mass of the black hole was measured and calculated through both Newton's second law and Newton's universal law of gravitation. In order to calculate the mass of the black hole, a few parameters about the star's interactions had to be known. First, the mass of the star is equal to 1.9890 times 10 to the 30th kilograms. Second, the black hole's position is 2 times 10 to the 10th meters in the x direction and 4 times 10 to the 10th meters in the y direction away from the star's position, which is at the origin 0, 0, 0. The last vital parameter which would be used to calculate the black hole's mass is the amount of seconds in 1 Earth year. This value, 86,400 seconds, was used as the time step, delta t, in the VPython computational model. In this experiment, the stardata.csv file was read in order to calculate the position of the star as it orbited the black hole at each delta t time step. These positions as a function of time allows one to calculate the velocity of the orbiting star. So as the star orbits the black hole of unknown mass, the velocity changes due to a net force acting on the star. As a result, delta V is equal to Vf minus Vi. One can now use delta V in order to calculate delta P, which is a result of delta V times the mass of the star. As it is shown below, Fnet in this experiment is equal to the change in momentum divided by the change in time. This means that as the velocity and momentum of the star changes during orbit, so too does Fnet. Furthermore, Fnet changes because the parallel component and perpendicular component of Fnet change as the position of the star changes about its ellipse. By vector addition, it can be proven that Fnet is equal to the sum of Fnet parallel and Fnet perpendicular. In order to create a computational model of the star orbiting the black hole, one had first to consider the parameters of the experiment. Shown here are the star's mass and the delta t time step as given by WebAssign. The next step was to read the stardata.csv file in order to determine the changing positions of the star through its orbit, which as a result changed its velocity as mentioned before, which yielded delta v. This delta v was used to calculate delta p, which we then said is equal to dp dt and Fnet by this relationship. P hat was multiplied by the magnitude of dp dt in order to find dp dt parallel, which we set equal to Fnet parallel. Through vector addition, we were then able to say that dp dt perpendicular is equal to dp dt minus dp dt parallel, and again we set this one equal to Fnet perpendicular. The arrows that were used here represent Fnet, Fnet perpendicular, and Fnet parallel are shown in the visual window as the code is run. And you should note that this second output of the print statement is the magnitude of the net force, which will be used to calculate the mass of the black hole. Because Fnet is now known, the mass of the black hole can be determined via Newton's universal law of gravitation. The constant g is equal to 6.67 times 10 to the negative 11, while the magnitude of r squared is equal to the square root of the x position squared plus the y position squared. The mass of the star is known to be equal to 1.9890 times 10 to the 30th kilograms, and Fnet, as mentioned just before, is equal to 1.5112 times 10 to the 27 newtons. As a result, the mass of the black hole was found to be 3.9803 times 10 to the 34th kilograms. This experiment accurately predicts the mass of the black hole according to the parameters which are considered in this enclosed environment. Note, this may not correlate exactly to real-world examples. Shown here is the code which correlates with Newton's universal law of gravitation in order to find the mass of the black hole. This is printed here as the last output of the print statement, in which, like I said before, correlates to the mass of the black hole. What does it mean? In this experiment, the sole force acting on the star is the net force which changes the star's momentum as it orbits the black hole. This net force is caused by both the parallel change in momentum and the perpendicular change in momentum. As a result, Fnet is equal to delta p divided by delta t. Likewise, dp dt parallel is equal to Fnet parallel, and dp dt perpendicular is equal to Fnet perpendicular. If this experiment was run with an actual star and black hole in our solar system, it would not be safe to assume that Fnet is solely equal to dp dt. There could perhaps be an electric field force or a slight gravitational attraction from other celestial bodies in the solar system which would alter Fnet. What if? It would not be possible to tell if there were any differences in black hole-star interaction if the motion of the orbiting star appears unchanged and if the gravitational attraction was the same as before in the case where a new black hole was placed in the same location as the original black hole. The new black hole would have to be identical to the original black hole in this scenario. It was proven that Fnet is equal to the change in momentum divided by the change in time. Fnet parallel is equal to the parallel component of the change in momentum divided by the change in time, and Fnet perpendicular is equal to the perpendicular component of the change in momentum over the change in time. Also, as the star's position changes, the net force acting on the star changes due to a change in momentum. And most importantly, the mass of the black hole was calculated through Newton's universal law of gravitation and determined to be equal to 3.9803 times 10 to the 31st kilograms.